to my presentation about the interlaminar fracture toughness behavior of prepreg laminates studied by in situ mechanical tests. I'm Simon, I'm with the University of Beirut. This is the city which is famous for the Wagner festivals. Probably most of you are too young for it, but some may know it. And today there are two things at least that are a bit crazy about this talk. One is about that it's not about methods, the other one is there's not a single equation in this presentation. I hope you're still not disappointed, but as you can see it is about the delamination behavior of fiber reinforced composites. And as most of you are more familiar with metals, just a very short introduction, what's a fiber reinforced polymer? We have the fiber which is responsible for most of the stiffness and strength. The matrix is responsible for the distribution of the stresses, and the interface which is important to the load on the fiber. And why is the fracture mechanics of this material is important? First is, this material is very sensitive to delamination, so even small objects with low weight can destroy its materials. It's important to understand the fracture mechanics, and toughening mechanism is to prevent such damages. So one of the most important tests works as follows. You have a bar-shaped composite, and you have several marks on it, and you can determine the crack which is growing from left to the right and putting forces on the left side of this bar. And by measuring forces and the crack length, you can define fracture toughness of this material. I hope you can see this from the last row. The crack is growing from left to right. So there are different mechanisms to toughen this material. One is to incorporate a filler in this material, in the matrix of the material. So for example, carbon black, which has been used here. You can see that without the interleaf you have a fracture toughness of 161, and with the interleaf of 242. And you can see different behavior. This might not be very familiar to most of you, but you can see that there is toughening behavior. Another mechanism is to use thermoelastic reels. So to use a conventional prepreg, which is just reinforced with a reel. So you have different layers of your prepreg and your reel. You can see that there's also a very huge increase in the fracture toughness of this material. And Beckerman said in his presentation, or wrote in his presentation, that while the toughening mechanisms of these types of systems are still not fully understood, it is believed that nanofibers act to bridge the microcracks which form in the interlayer. So I guess I don't want to go too much into detail, but the interesting thing is that the toughening mechanisms are not fully understood. And so the aim of this research is to improve this understanding of interleaved and fiber reinforced composites. So first with the toughened one by some interleaf, and secondly toughened with some filler. And materials may not be very interesting to you. We process the material for our prepreg line, so we have a special machine to do this fiber reinforced prepregs and then laminate them. So this is the second step. We first discuss the filler, then have our prepreg reduction with this machine, and then have the laminates. So we have different sheets. One is, as I told you, with the graphite filled laminate, and the second one with the polyester interleaved laminate. And now the interesting part, which might also be interesting for most of you, we have a module, a miniature testing module, which can be used for different tests. You can see here, smaller part from here might be used for 3-point bending tests or similar tests. You can also use this for tensile tests, for 4-point bending tests. You can use this for compression tests, for really all kind of tests. Just have probably to design tools like I did here on the right side, which can be used for a specific test. And this miniature testing device can be placed into the SEM to observe the fracture behavior of these materials. First results, which I got from the static test, or course the static test. So first I had my unmodified material, then one of the graphite matrix, And then the interleaved one, you can see that there is an increase in the fracture toughness of these materials. And I said, so this material is comparable by fiber building content to have comparison of these materials. Now you can generate these videos from SEM. You can see again that the crack moves from the left side to the right side. I speeded up this video by roughly 8 times so we can see something. This crack then slowly grows. I guess one can improve the quality of this picture by running it slower, but to have a comparison to the quasi-static test, I ran it at the same speed. So this is just a very basic observation of the neat material. When you have look from lower magnification, you can also see that the crack is really straight moving to the material. Also at higher magnifications, you still see the crack is quite straight. Then when you have the modified material, slightly higher fracture toughness, you can also see the crack moving from the left side to the right side. But you can hopefully see, okay, I see it on the screen, but don't see much on this screen here, unfortunately. I guess I go forward a bit. Okay, yeah, there's really not much to see from your side. I hope you see the bit that here the crack is moving and it's undulating, so it's not a straight crack. It's better viewable hopefully here in this picture. So you don't have to see straight crack that you could see before, observed before, but you have some undulation in your crack. And this is much better viewable at higher magnification. You see you only have this rather low increase in the fracture toughness, but for the other material, so for the material with the thermoplastic interleaves, you can see that there is, I guess it's better. You can see the crack is growing, and you can also see it's undulating, and at some parts there's new cracks starting. So here, for example, there's a transition of the crack, and the crack is starting at another point of your material. So you can also see in the other pictures low magnification. So here you see the first crack, second crack, and we call this crack pinning. Here also with high magnification, you can see the first crack stops at this interleave and starts to grow at another point. So this is already the summary. I know most of you are more familiar with methods, and probably you have an idea how to transfer these results to methods, to method forms or whatever. I guess there are a lot of possibilities to use this kind of testing device. One can see here in the presentation that the crack deflection with the graphite filled material is detectable by the in situ SEM fracture test. You can see some crack pinning, crack transition with the interleave layered one. And in further investigation, I guess that this method can be transferred to other tests. These are tests that are more used for composite materials, but I guess, as I said, it can also be used for methods. Then thank you for your attention. Thank you for my colleagues who worked in this project, and hopefully see you at the next one.